In this lesson, we're going to look more in depth at the structure and function of carbohydrates. We are going to identify the functional groups of carbohydrates and going to learn the general classes of naming carbohydrate molecules. Carbohydrates are part of our diet and provide an important role in our bodily functions. Carbohydrates have the empirical formula of CnH2nOn, where N is any whole number. For example, we can have C4H8O4. Although originally they thought that carbohydrates contained water because the ratio includes 2 hydrogens for every oxygen, later work proved that to be wrong. However, the name carbohydrate, which stands for water, was already in use and has continued till today. Carbohydrates are an energy source for us, as well as a source of fiber. They help determine our blood type. They're an essential component of cell membranes, and they are also in heparin, which prevents blood clots. Carbohydrates contain either an aldehyde or a ketone. When we see an aldehyde, remember it's going to be at the top because it has to have at least one hydrogen attached. So we see the C double bond O, or the carbonyl group, and it has a hydrogen on one side and then the rest of the molecule on the other. For a ketone, we see that we have a carbonyl group, or C double bond O, with 2 R groups, which are chains of carbon atoms attached. When we see a carbohydrate with a ketone, we will see it on the second carbon. Although there are other locations it can be found, this is the most common position. Notice that in both of these examples of carbohydrates, which will also be true in every carbohydrate molecule, there is one oxygen attached to every carbon. One of those oxygens will be a carbonyl, or a double bonded oxygen. The rest will be OH. And then, just like many other organic compounds, the remainder of the bonds are filled in with hydrogen atoms. One thing you'll see when you're looking at carbohydrate structures are some abbreviations that we use to indicate whether we're looking at alcohols or aldehydes. When we have an alcohol group, it will frequently be abbreviated as COH. When we have an aldehyde, it's frequently abbreviated as CHO. So you need to recognize this shorthand notation means something different for each type of molecule. Many of our carbohydrates have very specific names: glucose, galactose, mannose. However, you do not need to learn those. You should know the general names for carbohydrates, and those names tell us a few pieces of key information. It tells us whether a carbohydrate is an aldehyde or ketone through the prefix of aldo or keto. It tells us the number of carbon atoms by using one of the organic prefixes. Any of them can be used, but these are some of the most common ones that you will see. So if we have 6 carbons, we'll use the prefix hex. And the OSE ending tells us we're dealing with a carbohydrate. Let's look at an example of a molecule. This is a ketopentose. Now, there are multiple versions of ketopentose depending on the orientation of the OH and the H groups around the chiral carbons. However, we will group all of these into one class of molecules known as ketopentoses. The first thing we look is the keto, which tells us we have a ketone group, and so we're going to have that on the second carbon from the top in our chain of carbon atoms. Next, we see that we have pentose, and so we have 5 carbons in the molecule, so we use the prefix pent. And then we have the ending OSE, which tells us we have a carbohydrate. Note that in every carbohydrate molecule, there's at least one oxygen and a hydrogen attached to every single carbon atom. What is the name of the carbohydrate shown? In looking at the structure, we see that we have an aldehyde because we have the CHO abbreviation. So the name of our carbohydrate will start with aldo. Next, we count the carbon atoms, and we see that we have 7 carbon atoms, which means we will use the prefix hept. And because it's a carbohydrate, we use the suffix OSE. So the name of this carbohydrate or this class of carbohydrates is aldoheptose. Notice that this does not tell us anything about the orientation of the OH and the H groups. We can have many versions of aldoheptose, and they would all have their own specific name based on the pattern of OH and H on the left or right of the molecule.